Yeah, I'm happy now to try and put all the pieces that we talked about today together into a demonstrator that shows you how they interact and how this corresponds to our vision that we have for the ecosystem of how people can use all of these tools to do physics analysis. And what we're going to be using here is CMS Open Data, and specifically, we're going to be doing an analysis here with TT-VAR. There's various links up here that you are encouraged to check out if you want to see more about what the CMS Open Data is. What I want to highlight here, this is a technical demonstration. So our idea behind this demonstrator is that we want to do something that to a physicist looks like what they encounter in their day-to-day work. So we want to hit all the features that people will need in practice if they're doing physics, but we're not trying to do physics here with the open data. So that in particular comes out, for example, in our definition of systematic uncertainties. Again, we're trying to capture the functionality, but we're not claiming that we're doing now here some competitive TT-VAR cross-section analysis. So if you're interested in physics, please do check out the examples of physics results, for example, by Atlas and CMS. There's, of course, other physics results from LHC experiments and beyond, but do check them out if you care about that. What we care about here is a demonstration of functionality. Now, in this notebook, the analysis pipeline that we're using is summarized here in this first picture. We're starting out with columnar data that we're going to be accessing in various ways. We'll talk about this in a second. This columnar data will be filtered. We extract columns from it. We calculate systematic uncertainties, and ultimately we fill everything into histograms. We take those histograms, construct a statistical model, which we can serialize as a workspace, similar to the workspaces that we've just seen in the previous talk. Once we have that, then we can continue performing statistical analysis and looking at the outputs of that, looking at, for example, our nuisance parameters when we fit to data, plotting our statistical model, and so on. There's various packages involved here. I have some logos. We're going to essentially hit on all of these packages right now. And now in this notebook that we're looking at, there's 3 different data pipelines that we're going to be considering. And we're going to start with the first one. So what is this first pipeline? We're using purely coffee for columnar data processing here. We have columnar data from this CMS Open Data, which we pre-converted to n-tuples. And we use coffee to access the data, to process the data, and ultimately all of the different coffee processor instances that are running, which can scale horizontally, which is sort of implied here by this arrow. We can get more in parallel as we scale up. They will produce histograms. We aggregate those histograms, and we have a final big output histograms with many dimensions summarizing everything we have. This notebook has a flag pipeline, a variable to use, set that to coffee, which is the default in order to use that kind of pipeline. Then there's a second pattern, which we've briefly mentioned previously in Gordon's talk, where we again use coffee, but we use the service X processor in coffee. And what happens there is that service X will read our columnar data. It extracts the columns that we're interested in, can also apply filtering. And then as the data arrives from the service X transformers, it gets sent straight to coffee processors. And those processors, as the data starts arriving, process the data. And again, they build histograms. Ultimately, we aggregate everything and produce our final output. The advantage of that here is that since we pre-process data already in service X, coffee can have an easier job here. So I'm indicating this by these sort of blocks here being shorter, sort of a time axis. So the tasks are easier and faster to do. And in the end, we produce the same kind of output. Also, this is supported here. There's a setting for it as well, service X processor for this pipeline variable. And then lastly, there's one other pattern, which we'll briefly touch on at the very end here, where we're again using service X to do all the transformations. We aggregate all of the data from service X and have some small data set of all the relevant columns locally. And then we run standalone coffee, again, which we can then scale horizontally to process everything very efficiently, and we'll aggregate everything into a final histogram. Again, there's also pipeline setting for that. All right, and with that, let's get started. There's a lot to go through here. We're starting out by setting up our environment, importing all of the libraries. Many of these names should be familiar here of these libraries if you've been following the workshop so far. One thing to mention here at the very beginning is that this notebook is set up in a way that we can actually scale it quite a bit. And the way that we do this primarily is this setting that we will hit on in the next block, which is the number of files per sample. A sample here is a physics process. So for example, we're going to be looking at TT bar, W plus jets, all of those are different samples. And we set how many files in this open data sample, n-tuple files specifically, we're trying to process. Each of these files is about 100 to 200 megabytes. If we set this to 10, we're going through about 16 gigabytes of files. If we set it to 100, about 150 gigabytes and so on. So here, just to see what we have available, in total, it's about 3.5 terabytes of n-tuple data that are coming from something like 30 terabytes of mini AOD files. If you do have Atlas credentials, and then you can also access this data through Ruscio. And again, this is the full data set here. In total, we have something like 23,000 files almost, again, 3.5 terabytes of data roughly. So now we're getting to this block here, the cell where we're doing some global configuration settings. We're starting out here, we're setting the number of files we'd like to do per sample to 100 to a value of 100, meaning we're going to go through 150 gigabytes of data. Pure coffee, we want to scale with Dask. And there's a setting here for service X specifically. Depending on where you run, you want to set this variable here as well. Set it to local if you're running locally. If you're running at Fermilab, set it to EAF. We're running here at the Coffee Casa instance at the University of Chicago. The first thing in here, in this notebook now, and there's quite a bit of code, so we're not going through it in all the detail, is setting up our coffee processor. We've seen this previously, and the processor here is quite a bit more involved with the amount of code. And this is because we're trying to do lots of physics in this processor now. There's a few functions at the very beginning where we're defining systematic uncertainties, some simple ones that just have simple weight variations for different objects that we're going to be looking at. There's b-tagging variations that we're calculating, and we're setting up these systematic uncertainties in a way that they can depend on JetPT. In practice, they might depend on other kinematic variables, but just to see the pattern of how you might go about this, we have a jet energy resolution uncertainty here as well. And then the final processor. What we set up here that's important is our histogram. This is going to be where we aggregate all the output in there. It's a multidimensional histogram with multiple different axes. For the phase-space regions, we're looking at the physics processes, we're looking at the systematic variations we're looking at as well. And then the first axis here is the kinematic variable that we're going to be filling. We have some amount of metadata that we transport to our processor that we're going to need in order to actually make that processor work. And the first reason for why it needs the metadata is that we need to correctly scale our simulation to luminosity and scale it by the cross-section that happens up here. And then what ends up happening next is we're going to look at systematic uncertainties and do more event processing. This thing here is using a nice feature that was recently added to Coffee, this add systematics feature to nano events. So check it out. It's available in the latest Coffee version to attach systematics to events or to objects within events. There's a few more systematics that we set up here. For example, PT variations here for jets. This is related to something that we use to demonstrate jet energy scale, resolution, and scale variations. And we do this here at the very beginning because what we're doing subsequently depends on the properties of jets. So we do this at first, and then we check out what happens with all of these different variations. And then we're at our event selection. We're selecting electrons, muons, and jets with BT above 25 GeV. This should be looking familiar also. If you come back to earlier, remember earlier awkward and coffee talks. We apply event filters. We want a single lepton, at least for jets, out of which at least one of them should be B-tagged. We selected an arbitrary B-tagging threshold here. In practice, you're going to be using some value to achieve specific efficiency values if you're doing this. We apply all of our event filters. We have two different phase-space regions. One of them is for jets and one B-tag. So this is one B-tag less than you would expect from TT bar. So this is acting as our control region ultimately. And in this control region, what we're doing is we're calculating the scalar sum of JetPT, which is happening down here, which is also called HT as our observable. And the second region is perhaps a bit more interesting, our signal region, at least 4 jets and at least 2 B-tags, which is the phase space where TT bar lives. We select that event topology. And then what we do in here is we reconstruct the hadronic top. Using awkward again, building all the combinations of 3 jets that are possible in the event, ensuring that at least one of them is B-tagged, which is down here. And then we calculate the tri-jet mass of the system that has the largest PT, which is happening in this line down here. So what we're doing ultimately is we're looking at a system of 1B and 2 jets, maximizing the PT of that and plotting the mass. Everything else here is just filling histograms at the very end. So let's register our processor. The coffee schema that we're using for these open data events was already shown previously by Matt. So we're quickly going through that. And what we're doing down here is we're constructing our file set. This is all the data about the files we're trying to process. There's the different physics processes listed here. We have multiple different versions for TT bar, a nominal sample, which is point beta 8, and various systematic variations, and various other physics processes as well. You'll see there's a few not in here, for example, diboson and such, which certainly you would also like to add if you're doing this as a serious physics analysis. And then here's an example of the information in there. There's a list of files, and then metadata attached to all of these file sets. We're going to skip over this right now because we're not using service X now. Similarly with this, we're coming back to this later as well, which means now we're at the point of execution. We're hitting confirm here. We're in the coffee pipeline, and we have task enabled. So you can see here something is happening. Let's check out what is happening by switching over to a tab where we have task. And you see here still, this is some information left over from previously. We'll try to zoom over a bit. So what is happening now is the pre-processing step of coffee, where coffee is looking through all of the files, all of these 850 files that we would like to analyze. And you can see down here, we're going through that. We're already half through with pre-processing. There's 850 files in total, as I was mentioning. So we're looking through all of them. And once this is done, then we will do the actual processing, where coffee will then run the processes that we just looked through in order to do the analysis task at hand, which means for all of those files, it will calculate our observables in the phase-space regions that we have defined. And it will also calculate all the systematic variations and ultimately return histograms to us. So you can see now here in blue, the processors starting to run. And again, there's the same counter here, 27 out of 850. Again, the 850 files that we want to go over. There's also a reduced task down here, which is what we need at the very end. So we're scaling out the production of these histograms into all of these different instances of our processors running on our workers. And at the very end, we're trying to gather all of this information again into a single histogram object that we can then use for subsequent processing. So things are starting now, and usually it will take a few seconds, and then we're going to start scaling up and get a few more workers, which will then speed up this analysis task. Usually it takes like 2 minutes or so to go through this, and we can keep track of it here in this monitor with task to see what exactly is happening. Instead of just waiting and looking at that graph to complete, what we're going to do is we're going to look at one file that we're going to use in about a second. When this is done, you can see here again, the time is being tracked in the notebook as well. And that is the configuration file of the statistical model that Matthew already alluded to in the previous talk. And the reason why we're looking at this is we're building all of these histograms, and you might wonder, okay, but what are you even going to do with all of these histograms? Why are you building them? And well, we want to do a statistical analysis. And we're using a cabinetry here in order to build a statistical model in this PyHF format, a hist factory statistical model that we can then perform inference with. And this configuration file here is the configuration file where we set up our statistical model. So up here, there's general pieces of configuration required by cabinetry in order to construct the model. We point to the histograms that we're going to be building. And then inside those histograms, inside this root file where we're going to save everything into in a minute, there's different histograms with different names. These things up here, they are placeholders. So region path is a placeholder that tells you what the region is called. And then there's a list of phase-space regions. for the forget 1b selection, forget 2b selection, and they each have different values for the region path option, which then gets filled in here. So all the histograms for this control region are going to have a name starting with forget 1b, for example. So this is the phase-based regions that we want to look at in our model. Then there's also the different samples. We're not looking at data here. This is purely simulation-based, so we're going to be building a set of pseudo-data instead. And then there's different physics processes, TT bar, W plus jets, single top in S&T channel, and WT as well. And besides all of those samples, the reason we're building so many histograms is that many of them are for systematic variations. We have some systematic variations we define down here that only act on TT bar, which is what we denote with this setting here, that we only want to apply the systematic variation on TT bar. This is a variation of the matrix element where we switch power PK8 to MC at NLO with PITHIA 8. We have a path shower variation for TT bar. We have various scale variations for TT bar. We have our jet energy scale and jet energy resolution uncertainties, various speed tagging uncertainties, and others. So we enlist them here in this configuration file. And then ultimately, the last thing that's of importance is we have a normalization factor for TT bar. And that is the thing we want to measure. We want to measure how our cross-section for TT bar compares to the standard model prediction. Let's switch back to the notebook. All right, it's a bit slower than previously, but we're getting there, about 65% done. Let's see whether we have scaled a bit in the meantime. No, things are still running, but that's fine. We're going to come back to this in a second. And let's already take a look at what we're going to be doing next, so that when we run these next steps, you're already prepared for what we expect to happen. So we're building all of those histograms. And as you might remember from the processor, let's have a look at it again. Up here, we have defined this histogram, which we aggregate all the information in, that has various different axes. One axis for kinematics, an axis for the phase-based region, an axis that we automatically fill, that's with this growth keyword argument here, for the different physics processes, for the different variations. So when we fill this multidimensional histogram, one thing that we might want to do after filling everything is actually looking at what is in there in order to sanity check that what we have constructed here makes some sense, and that indeed the output is useful for the physicist. So this is the first thing we're going to be doing. There's a small utilities function. You can find others in this utility model that's also included in the repository, where we just do some simple styling. And then once we have the histogram, we can start looking at it. And what we're using here is this thing called UHI, Unified Histogram Indexing, I believe, in order to work with this histogram in a quite convenient way. So our first axis here is the kinematic axis. And what we're doing here in this command with this sort of J is that this axis is binned in GeV. And by saying 120J, we're going to be only looking at events with 120 GeV or more. And we're also going to rebin. So this is everything here just happening with these nice UHI features. We're going to be looking at a specific phase-based region, all of the processes, only the nominal variations. So our job is done, about 5 minutes, and we can plot it. So down here is our control region. You can see lots of TT bar, as you might expect, decent amount of W plus jets, as you might also expect, given that we only require one VTAG. Let's sanity check our signal region. And this is the place where we built our reconstructed hadronic top, the mass of this BJJ system. You can see a nice mass peak in the TT bar spectrum around the TT bar, around the top mass, which is what you would expect. So things seem to be working. Also, you see everything is dominated by TT bar, also what you'd expect given this selection of phase space. So nice, our histogram, at least for the nominal case, seems to be working nicely. Let's take a look at systematic variations. Here we're plotting the different B-tagging variations. Again, we can see they have some impact on our kinematics. Jet energy scale similarly has a very small impact only in the way that we defined it, but also does change our distributions. We're saving everything to disk now, so that we have all the histograms available in this root file, histograms.root. And now it's time to perform inference. So we're loading this configuration file that we've looked at just a minute ago. And what cabinetry does is it now collects all of the template histograms that are required by this configuration file to build a statistical model, which is this line down here. Optional post-processing, which isn't required strictly for this case, but it's generally something that you might need. And then when we have all of the histograms available, we build a workspace. We also save it to disk here in case we want to use it afterwards. And this is a workspace that you can feed straight into PyHF. One thing you can do is you can inspect what's in there, which we can do with the PyHF command line. There's two different channels, our Forget 1B and 2B regions, multiple samples and parameters. And you can see also here which samples are in there. Those are the ones that we were processing earlier. Okay, let's now perform some inference. We're using Carbonary to perform a maximum likelihood fit, again, running through PyHF, looking at the polls that we get out. If you're a physicist, you might be scared looking at those polls. No worries. Again, we're not trying to do physics. We're going to try to adjust this example a bit over time so that it looks a bit more realistic and not super scary for a physicist. But the fit is working and we're getting out what we put in here. Let's see what we get for our cross-section for TT bar. We're spot on actually with the standard model. Our normalization here is spot on 1 plus minus 14% roughly. And now that we've run a maximum likelihood fit, let's see what we actually fitted. These are the pre-fit distributions. You can see fairly large uncertainties. You can see a bit of a data Monte Carlo disagreement as well. Data here being pseudo data that we built from various TT bar samples that we're processing. This is the control region and this is the signal region. You can see the binning is slightly different here. Again, we adjusted the binning as we were doing this, as we were saving the histograms. Let's take a look at the post-fit modeling as well. And you can see now everything is spot on as you would expect from this maximum likelihood fit. We nicely fit the model. So everything here is in good agreement. So all right, this was one path through the notebook. And I'm briefly going to show you now two other ways of going about this processing pipeline that brings you all the way from the inputs to the final statistical inference and the final results. And to do that, we're going back up and we're going to switch this to just a number of 10 here in order to be fast and safe for live demonstration purposes. And we're changing the pipeline to the service X processor pipeline. And we're going to start running everything. And what does this mean when we switch? That means we switch to the second pattern that I'm demonstrating here in this figure. So we read data with service X. And as the data arrives, it gets fed to coffee processors that then aggregate the data into histograms. We're scrolling through to where the processing actually happens, which is down here. And as you can see here, for all of our histograms now, we're going to process 10 files. That's 0 out of 10. And they start already being processed and start arriving. We have our Service X dashboard open over here, which I'm going to refresh to hopefully be able to see them. As what you see here are earlier queries. Let me try to, the page is loading. So you will see on this, right, here we go. You can see on this, the tasks, all of these different tasks with 10 files each to process. Some of those are already complete. Some are currently being processed. So Service X is doing our data processing, sending it back, and then as the data arrives, the coffee processors run over that data and process that data to ultimately give us the results that we're looking for. And again, allowing us to build, to aggregate all of the histograms into a statistical model and to perform inference with that. So as you can see, things are still running, but we're already sort of in the tail of our job. Many are done already. So we're getting to the end. Let's switch back to our notebook, where we also see now the final tasks being wrapped up, the files being downloaded. And then once they're already downloaded, okay, it looks like this bar froze because it seems like the execution is already through. So, all right, something broke in the progress bar, I assume, but not a problem. We're running again the subsequent steps. You see, this histogram is going to look slightly different now because we're only running over 100 files instead of 850 files total. So again, we have the same histograms. We can look at all the same plots because we built the same type of histograms, and we can visualize everything again. Again, our fit still agrees. So this is a different way of going through this. And this time we made use of Service X, followed by Coffee to process all of our data. And then I will briefly show you one other aspect here of this last pipeline that we're demonstrating in this notebook. And I'm only going to show you the first piece of it here. There's some bottlenecks in this pipeline that appear in practice, which now, now that we found out about them, we're going to address. So this is some of the work we're looking at doing next. And for this, there's one other setting that we changed here, and we switched to service X data binder, which is now the method of using this specific library, this service X data binder library. And if we do use that, then we're hitting this cell down here in our notebook. I should briefly mention what I forgot just now. Previously, when running through service X, we needed a query to get all of the outputs actually that we wanted to feed to Coffee. Our query here was very simple. We didn't apply any filtering, but we only selected the columns that the processor needs, which are those columns here. So this is the query we just used in the previous demonstration when feeding service X output straight to Coffee. All right, and then now that we've set our pipeline to service X data binder, let's get this started. We have a more complex query, which we'll go through now as this job is running. And there's all of these different physics samples. So if we went through all of that, that's about 3.5 terabytes. For demonstration purposes, I will only do a small subset of this with about 114 files, I think. Going through all of that takes something around 10 to 15 minutes at the moment. But let's be safe for the purposes of demonstrations. So we're launching that. We have this data binder configuration, this dictionary here, which has a few general kind of settings, and then a list of samples we want to process. Those samples are pointing to the Ruscio data sets that are given at the top of the file. And then what we're doing with these samples is we're running this query that we've defined up here. And what this query does ultimately is it selects the same type of columns that our processor needs. That's the last step here in the select. And before that, it applies quite some filtering. So the first filtering up here is a filter where we want to count electrons with a PT of greater than 25 GeVs and add to that muons with a PT of greater than 25 GeVs, and only accept events where we get exactly one. So either one electron or one muon. There's also a filter here in the next line where we want to count jets, and we only take events where there's at least 4 jets with a PT of greater than 25 GeV. And the next line here is also to ensure that there's at least 1 jet that is BTAC. All right, this is already done. So this is reminding me of Gordon. We are hitting our processing quicker than we can get through it. If we go back to the dashboard, you will see now that there's going to be a new entry for the process that we just ran over. This page will take a second again to refresh. You see, indeed, it's up here. Service X data binder also gave this a nice title here. This is the sample that we processed, 114 files. And now we have this data available locally to us, and we can use it subsequently to process it. And if we process this data instead of processing directly from the n-tuple inputs, then we would generally expect that we are faster in our subsequent Coffee processing step because we already filtered out the data and we only have those events available that we really want to process. So there's some time to be saved here when running the Coffee processors over that. All right, with this, I'm at the end of the demonstration that I wanted to go through today. But before we move over to questions, one last thing here to say at the very end, what's next for this demonstration? And that for us is, at first, making this even more feature complete. I think we hit on quite a few things that you're going to run into in your day-to-day physics analysis needs already. But we would like to keep expanding this, addressing performance bottlenecks to make sure that we can demonstrate this scaling very nicely at very large sizes of input data. We only went through about a few hundred gigabytes of data today in this demonstration, but we intend to keep scaling this up. And lastly, we're very happy to collaborate with you. So if you're interested in this effort, then please do get in touch. If you would like to implement some of this with other tools, if you're interested in any other way, please do get in touch. I have again linked here the contact information. Feel free to contact Oksana and me directly as well. And we're looking forward to working together with you. And before we close, though, for today, there's some time now at the end for questions. So any sort of questions or other points you would like to bring up, we'd be happy to address them now. Thanks.
Matthew?
That was a super nice talk, Alex, by the way. So I have a very kind of silly question that I think I should know, but while you were running with the Service X processor, you were able to also show a view of like the Service X usage. Can you just show that again, or remind me how one actually where one actually goes and views this? This is just on the ServiceX website.
This is site specific. So this is the ServiceX dashboard, and this depends on the endpoint. So this is running now against the University of Chicago endpoint. You can see the URL up here. I think it's also linked from the sort of entry page at UChicago. I believe at the moment, this website isn't working yet for Coffee Casa. We're working on getting that also running there so that you can have the same type of overview over your queries in Coffee Casa ServiceX instances as well. But generally, the URL is going to depend on the instance that you're running against of ServiceX.